Vitamin B3. It's a water-soluble vitamin. It's also known as niacin or nicotinic acid, and this means the fact that it's water-soluble, it can be transported around the blood through mediums such as blood plasma, which is basically mostly made up of water molecules. Yet vitamin B3 can be produced by the body, and this essentially defies the whole definition of what a vitamin is. A vitamin is something that can't actually be produced by the body, yet is needed for essential metabolic functions to actually be able to sort of sustain yourself. And this is why if you don't eat enough vitamins, you end up being deficient, and you end up sort of suffering because you're in pain, and you have a lot of diseases, etc., going on inside of your body, which just isn't good for you whatsoever. And while vitamin B3 cannot be produced in large enough amounts to actually sort of sustain yourself and not cause vitamin B3 deficiency, also known as pellagra, it still can be synthesized. And so I thought I'd go through how vitamin B3 is synthesized from the molecule tryptophan, and then what vitamin B3 actually does once it turns into vitamin B3, or is vitamin B3 inside of the diet. And the first reaction step inside of the metabolic pathway of vitamin B3 is tryptophan, as I said before, and an oxygen molecule turning into N-formyl kynurenine, and the enzyme that catalyzes this reaction is tryptophan pyrrolase. And then once you have N-formyl kynurenine, this second reaction step of this metabolic pathway, you take that N-formyl kynurenine, add it to a water molecule, and then you just get straight up kynurenine. And the enzyme that catalyzes this reaction is kynurenine formylase. And you know how I've mentioned in previous videos about ATP, ADP, NAD, NADH, NADP, NADPH, all of that sort of stuff. There's you know I've said about ATP ends up turning into ADP and adds a phosphate group onto the products. The thing that I'm about to mention and talk about ends up kind of doing the opposite. You have a molecule of THFA. I can't remember what it stands for, but I'll put it up on the screen. And this ends up turning into 4-mil THFA. And that's where the N-formyl sort of ends up going to actually make kynurenine. Now, once you have kynurenine, the third step of this metabolic pathway reaction process, synthesis of vitamin B essentially, you take that kynurenine to produce hydroxykynurenine. And on the left side of this reaction, you have an NADPH molecule, and on the right side of the reaction, you have an NADP molecule, because the H part of the NADPH is needed to actually make it a hydroxylase, because the hydroxylase has an OH group. And yeah, it's all very complicated science. The way that sort of works is more sort of chemistry rather than biochemistry, and these sort of metabolic pathways mostly focus on biochemistry. But maybe once I sort of learn more about chemistry within the sort of school system, etc., I'll be able to kind of report back to you on how these sort of nucleophilic attacks, etc., free radicals, whatever, actually end up working to actually make these metabolic reactions, biochemical pathways, actually end up working in the end. And the enzyme that catalyzes this reaction is kynurenine hydroxylase. And the fourth step inside of this metabolic pathway, this reaction pathway, etc., is 3-OH kynurenine, which is essentially just another way to represent hydroxykynurenine. The 3-OH, OH essentially means hydroxy, hydroxyl group, etc. That's more sort of chemistry. OH simply sort of means hydroxyl when you sort of compare symbols to words. And this ends up producing 3-OH / hydroxy anthracic acid plus alanine. Alanine is a side product, and this reaction is catalyzed by the enzyme kynureninase. Now, the fifth reaction step inside of this metabolic process, you take your hydroxy anthracic acid and you end up converting it into a very complicated molecule with a very, 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 very long name. And I'm going to simply abbreviate it and maybe put the text up on the screen. 2A3C5MSA. That's the whole abbreviation. I'll put the actual name up on screen, but this reaction is catalyzed by the enzyme hydroxyanthracic acid oxidase. And what's interesting is that sort of massive long name that I talked about earlier, that is the product that doesn't really end up getting produced very often. 3-OH hydroxyanthracic acid can also go through a separate metabolic pathway in a few other separate places inside of your cells that end up producing acetyl coenzyme A, which, as I said before, is a very, very useful molecule. I've said that in multiple videos. Acetyl CoA is needed to produce things like cholesterol, goes through the Krebs cycle, all these sort of really, really important things. And that is essentially why the sort of vitamin B3 synthesis, there isn't really enough niacin to be produced to end up sort of being sufficient and to you to not need it in your diet, because once you get that really long named molecule, that ends up only being produced like 3% of the time, and so you don't get as much vitamin B3, considering tryptophan is a very common amino acid that's inside of a lot of things like meat, protein, beans, pulses, etc. Now, step 6 inside of the vitamin B3 synthesis reaction process is that really long named molecule I talked about earlier, 2A3C5MSA, ends up turning into quinolinic acid plus H2O. This reaction doesn't actually end up needing an enzyme, it simply goes through a process known as spontaneous cyclization. I'm not actually sure what causes spontaneous cyclization to occur. Maybe I'll put like a little paragraph to the left of me or right of me or whatever, and that will end up explaining what spontaneous cyclization actually is and how it actually works. But once you get quinolinic acid, that ends up producing niacin, and this reaction is catalyzed by the enzyme decarboxylase. Now, niacin actually has a different name known as nicotinic acid, and there's a reason that vitamin B3 is now known as niacin rather than nicotinic acid, and you may be thinking in your head, I think I might know the reason why that's the case, and that's because what exactly does nicotinic acid sound like? Nicotine. Now, nicotine is very commonly found in cigarettes, vapes, and patches, etc., pills, all that kind of stuff. It's a very, 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 very potent stimulant, and your brain cells will develop a reliance on it to actually get a little bit of energy inside of the brain cells, and it stimulates them, and you end up getting dependent. It's not a good thing at all, especially considering the other health effects that come with things like vaping, smoking, etc. It's not a good sign, but the thing is, I've previously talked about the sort of craze of smoking being popular and seen as healthy in the 1960s. That was the same period that vitamins started to kind of be discovered in our diets and the things that need to be necessary in our diets to actually kind of live a long and good life. Vitamin B3 was discovered as nicotinic acid. That was what it was named, and people associated nicotine with nicotinic acid, and this meant that they thought that cigarettes were healthy because they thought that it had vitamin B3 in them, despite the fact that nicotine and nicotinic acid are two very different things. One's needed for essential bodily functions, the other is a potent brain stimulant that causes a lot of health issues when you kind of combine it with tobacco smoke and the other vaping chemicals, etc. It's not good news, and yeah, that's why they ended up changing vitamin B3 to have the name niacin, because otherwise people were going to end up smoking cigarettes thinking it was healthy when it was actually going to end up causing them premature death. Now, once you have niacin/nicotinic acid, the main thing that niacin is used for inside of the diet is to produce NAD+. I've talked about NAD+ in a few of the sort of metabolic videos that I've done in the past, but the way that NAD+ is produced inside of the body is that niacin ends up turning into NMN, I can't remember what that stands for, I'll put it up on the screen, plus a CO2 molecule, and you also have a PRPP on the left side of the reaction, which ends up getting turned into a PPI molecule. I also can't remember what those stand for, and so I'll have to put those up on the screen as well. And this reaction is also catalyzed by the enzyme QPRT. I can't remember what that stands for either, but I just remember it was really, really long, and I couldn't actually fit it on the page, so I just decided to abbreviate it, and I'll end up putting it at the top of the screen, just like I've done with a few other enzymes in this metabolic process. But once you get NMN, you end up taking that NMN, and this is the 9th step inside of the reaction process, and you end up getting desamido NAD+. And on the left side of the reaction, you have an ATP molecule, and on the right side, you have a PPI molecule, just as you did with the previous reaction. Now, you take that desamido NAD+, and this is the 10th step of the reaction process, vitamin B3 synthesis, NAD+ synthesis, and this is the final reaction step, and this is where you end up with NAD+. You end up taking desamido NAD+, adding it to glutamine, and then you end up with NAD+ and glutamic acid. And this enzyme, just like the last one, has an ATP molecule on the left side, as well as a PPI molecule on the right side of the reaction. But as I said before, only 3% of tryptophan that is inside of our diets ends up being converted into vitamin B3. The rest is converted into acetyl-CoA through another metabolic process that I'll talk about in a separate video, but that is for another time. And yeah, that's what I found very interesting. That is the reason why there is not enough vitamin B3 synthesized by our bodies, and we still do need it inside of our diets to actually be able to function like a normal person. Vitamin B3, you need it to produce NAD+, as we've seen in this few little reaction step process. NAD+ can be used for a wide variety of things that it essentially just makes reactions work. I've mentioned in a few past videos how NAD+ on the left side turns into NADH. This reaction ends up producing energy, and NAD+, NADP+, NADPH, and NADH, all of that sort of stuff, it's very interesting. It deserves its own separate video. But the whole sort of NAD+, ATP, coenzyme A, all of these large molecules that, while nothing really happens to the baseline sort of molecule, the sort of things that happen at specific sites on the molecule is very, very interesting. It all deserves a video of its own. And I think there are a few other kind of molecules like ATP, NAD+, that sort of have this similar effect. But ATP and NAD+ are probably the things that the majority of reactions are sort of happen with NAD+ and ATP, because I know I mentioned earlier about the sort of THFA and formyl THFA. That's probably kind of works in a similar way to both ATP and NAD+, NADH, NADP+, and NADPH. It all works in probably a pretty similar way, including like the PPI I talked about earlier. But it's all a very interesting thing. These kind of reaction things that aren't really sort of catalyzers, they aren't the enzymes, they aren't the big things that are made out of a lot of protein. They're kind of the coenzymes that sort of mean that the thing can actually be sort of split, or the reaction can actually be processed. And it's a very interesting thing that I'm going to go through in a whole separate video, because trust me, it's interesting and it definitely deserves one of its own. But with that, I hope you do end up getting enough vitamin B3 in your diet by eating a wide variety of foods in a balanced diet. And with that, I also recommend subscribing, because I love this community of young tribal people who are willing to improve themselves so much more than they already have. And good luck.